Let us begin with a life scene. You walk into a tiny studio apartment. There is one bed, a table, and a small storage. Yet somehow everything fits. In the night, the bed becomes sofa, the table folds into the wall, the suitcases fit under the floor panels. You invite guests and nobody feels the space is small. What you witnessed is the illusion powered by smart management. And computers do the same with the memory. Even if they have small RAM, they make programs feel like there is plenty. Like a magician who pulls a never ending ribbon from the hat. And that's the trick called virtual memory. And today we will try to uncover that magic. We know that computers live in two worlds, the physical world, that is real RAM, the chip, and logical world, the imagined large memory. Virtual memory connects both worlds like a bridge between a village and a metro city. A train with, say, 50 seats, but it is serving 100 passengers by rotating. No one knows how they swap. Let us say a WhatsApp group, which seems huge, but the server manages it in limited hardware. Nobody sees the limitation. It's only the experience. And that's the role of virtual memory. Make small hardware look huge. Let us stretch this imagination and try to address why virtual memory is really required. Think of the biggest supermarket in your city, say Pune. Even though the stock is limited, they use shelving tricks, which makes that it looks full and organized. Simply, in similar world, one can see this in your computer too. Applications larger than RAM still get the room. Many applications runs at the same time. Every program gets its own private memory view and applications run perfectly. When you open a browser, and let us say that browser you have opened 12 tabs, there is a music playing in background, a video call is going on, and your notes are open all together. And your 8 GB RAM, if you see, cannot fill all that directly. And that's where virtual memory comes into picture. Virtual memory makes it possible by providing an illusion of abundance. Imagine a very fast translator who hears a word in Spanish and replies instantly in Marathi before you blink the eyes. And that translator is your memory management unit. It converts imaginary addresses into real addresses. That is the memory addresses, like RAM addresses. It does this very instantly. It never asks for help. It operates faster than your heartbeat. Let us say you are typing in Google. Your brain believes letters appear directly on the screen. Behind the scene, MMU, that is memory management unit, is translating thousands of addresses or thousands of address operations per seconds. It is like oxygen, which always is there, never noticed, yet absolutely necessary. Let us use a kind of playful example. Now you might have seen children's do build castles using Lego bricks. Now each brick has the same size and same shape. They can replace one brick with another whenever required. And virtual memory acts or works like Lego only, where virtual pages are the identical building blocks and physical frames are identical slots where the pages fit. Any block fits anywhere. So rearranging it is very easy. Let us talk about the desks available in the school or colleges. Most of them rather are identical. Any student can sit at any desk if needed. And that's why memory becomes flexible, clean, and efficient. Think of the operating system as a hotel manager or probably a traffic controller or a reservation agent or a security guard. Like if you talk about these all examples, you will see that how operating system would be handling virtual memory. It performs multiple responsibilities, keeps memory tables for each program, decides which pages stay in RAM, moves older pages from RAM to the disk, and prevents programs from crashing or entering into another's memory. Let us take another day-to-day example you might experience in hostels. Imagine your hostel rector who assigns rooms. He moves students when visitors come. He locks rooms so others cannot enter. The operating system does exactly that with pages and programs. Let us move further and let us imagine that you visit a theme park. The park looks seamless, like lights, stages, clean paths, everything is there. Behind the scenes, if you really check, it is messy maintenance zones, fences, cables, but we never see them. We just see lights, stages, and clean paths. Every program gets a similar experience. It believes memory starts at zero. It thinks it is exclusive owner of that particular area. Never sees physical fragmentation. Never sees the storage scattered everywhere. The developers enjoy this illusion. They write code without worrying where their data physically would be sitting. And that's the thing. Like virtual memory hides complexity, like curtains hide backstage clutter. Now let us try to understand the important concepts like demand paging and swapping, which is kind of minimalist philosophy that one should know. Let us think of a Netflix movie, an OTT platform. It does not download the full film at once. It streams only what you watch, and computers do the same thing. It loads the program into RAM only what is needed now. It pushes inactive parts to the disk. It brings them back when needed. Let us take example of an hotel. A chef keeps only required ingredients on the table, storing others in the pantry, bringing something out only when the recipe needs it. And this trick lets the computers run more application than RAM normally supports. Now, when the show goes wrong, why exactly the slowdowns happen? Why the computers become slow? Let us imagine a person constantly moving clothes between cupboard and a loft. Instead of getting dressed, now what he is doing? No task gets done. The task is just shifting the things. And that is called thrashing in memory. Too much swapping. And because of it, your disk becomes busy. And at some time, at some point of time, your system freezes. What would be the solutions? Solution would be like, for example, adding more RAM. That is like considering the example of the person which we discussed earlier about moving clothes, increase cupboard space. Secondly, like close all unused applications, and that means reduce the clutter. And lastly, write the efficient code. That means pack the things neatly so that everything fits into cupboard. Let us take another example. Your mobile slows down when you run too many applications. Most of the applications are in background. Now, if you close them one by one, your phone becomes responsive, and that's the classic memory relief. Now, let us try to imagine virtual memory aspect, how the operating systems are really carrying out. Let us take example of Windows. In Windows, there's a helper file called as pagefile.sys. It's like a butler storing overflow luggage. It stores extra memory pages, lets many applications run. It moves data quietly without even telling you. You can open, say, Photoshop, MS Office, Teams, and Chrome without crashing because Windows secretly shifts memory to page file. And this background service gives smooth computing. And as it happens automatically, your big computer you SIM as a smooth, accessible device and usable one. Now, if we talk about Linux in Ubuntu, it is kind of a librarian model that it makes use of. Ubuntu has something called a swap space. Let us imagine a library. The popular books stay on the front shelf. Less read books are moved to the storage room and room stays tidy. Readers get books without the delay and Ubuntu follow the same behavior. RAM is used for active applications and swap space is used for sleeping applications. And all this movement happens silently, like a disciplined library system. Let us appreciate this full magic. Virtual memory makes small to look big. Software and hardware cooperate while using virtual memory. Computers run many applications at once. Programs feel they own huge memory and users feel no limitation. The cities with limited land but tall skyscrapers house many families are staying. Virtual memory does the same, stretches capacity without increasing physical size. Computers are not strong because of their size, but they are strong because they think smartly. With virtual memory, a small device acts as a big. A tiny RAM behaves like a generous model. Applications feel free and users feel rich. And that is the magic we unlock when we understand virtual memory.